Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening, everyone. Good afternoon. Welcome to our ECE seminar series, where we host and invite distinguished professors, as well as professors from within KU, from outside KU, and even any experts in a specific topic for this weekly meeting and this weekly ECR seminar. Where we sit together and share knowledge and share expertise. So today we would like to welcome Professor Qamar Abbasi. Professor Qamar is a professor of applied electromagnetics and sensing at the James Watt School of Engineering, leading the connecting people theme and directing the communication, sensing and imaging hub in the UK. He also advises the UK government's Department for Science, Innovation and Technology, and manages about £13 million grant portfolio with over 500 plus publications and 11 books and multiple awards, mashallah, including the UK Exceptional Talent Endorsement. And he has been featured by BBC, Scotland TV and others, and also an IEEE senior member, where he chairs also the IEEE APS and MTT UK Ireland Scotland chapter. He also serves as an editor for IEEE journals and holds several leadership roles in IEEE and IET. His topic today, titled Reconfigurable Intelligent Surfaces, RIS, for communication, sensing and localization. The reconfigurable intelligent surfaces are a key technology for next generation wireless networks, enabling precise control of electromagnetic waves for communication, sensing and localization. So I'm not going through the abstract, as probably many of you have seen the abstract in the ad. So please join me welcoming Professor Qamar in this seminar. Please, Doctor, go ahead.
Thank you. Thank you so much. Feeling.
We love you.
Thank you. Thank you so much. Thank you. So my talk is about 6G, and the format is that initially I'll tell you about University of Glasgow, and then why we need 6G, and then I will be talking about one of the enabling technology for 6G, which is intelligent reflective surfaces or smart surfaces. So for the knowledge of students, if you don't know where University of Glasgow is, basically it is one of the fourth oldest university in English speaking world, established in 1451 after Cambridge, Oxford, and it's somewhere in the north of UK. And it is home to various Nobel laureates, including James Watt, John Logie Baird, who made the television, the Nobel laureate for 2021, David Macmillan, was University of Glasgow alumni as well. It's top 100 university in the world and has various transnational engineering programs. I lead this hub called Communication, Sensing and Imaging Hub, which has more than 140 researchers from 28 different nationalities working on all layer of protocol stacks, starting from devices going up to application layer. And it houses National Scotland 5G Centre, the 6G hub, Cheddar hub, and so on. So let's go back. I'm sure many of you were not born when 1G came. It was back in 1980s. And every 10 years, we have a new generation of mobile communication coming, and each generation was better than previous generation. And the real change happened when we had 5G, because we started talking about connecting an ecosystem. So up to 4G, we were talking only about mobile communication, mobile to mobile connection. But in 5G, we started talking about connecting everything by using IoT, your home appliances, so on and so forth. And then 6G came. And the real feature for 6G is that up to 5G, you can do only communication by using mobile or the mobile generation. But with 6G, you can do both communication and sensing, which I will talk about that in detail. But the question is, do we really need 6G? This is a big question, because I can watch movies, I can do anything by using my even 4G as well, and 5G can give me better speed. So I have to make the case that do we really need 6G, and then I'll talk about technical aspects. So number of mobile users are increasing day by day. Around 67% of the global population is using internet, and an average user is spending 6 to 7 hours on using mobile data, which is very big. So the demand is increasing. But this demand can be fulfilled by 5G as well, right? But I was in Mobile World Congress last year. So what happened that for first time in history since mobile technology inception, the operators and vendors were not getting return on investment. Means they put money, so they want huge profit, but they were not getting it. Because the challenge is that, as I said, whatever 5G can do, 4G can do that as well, because there were not any use cases which explicitly needs 5G, and money return come from those use cases. So there was some flaw in designing mobile networks up to 5G. And what was the flaw? That the researchers set up the KPIs, they make a network, and then there were no use case outside, for example, for 5G. So we started thinking that let's go the other way around. Instead of setting KPIs for 6G, let's think of some use case first and then set up KPIs according to that. So we came up with a very interesting use case, that how many senses we humans have. Can somebody tell me? 5. But people like Dr. Sami has 6 as well, but normal people have 5 senses. So up to now, we can transport 2.5 senses from point A to point B. Hearing by using mobile phone, vision by doing video calls, and you have seen haptics by using robots, right? But we are unable to transport smell and taste. So imagine if we teleport all 5 senses from point A to point B, then you can have a holograph with all the 5 senses. For example, I can have a taste of any Saudi dish while sitting in Scotland with same aroma and same environment. So that is teleportation of all 5 senses from point A to point B. But this needs ultra low reliability, ultra high throughput. For example, 1 inch square meter of hand needs around 10 gigabits per second of data, and imagine if it's a complete hand, how much data it needs. So this means that 5G cannot fulfill these features, the stringent requirement for this use case. So we find something which needs 6G. But there are many other use cases for 6G available as well. And these are the elements of 6G which are under discussion. But one key feature for 6G is that it will be ubiquitous, that it can take decisions itself to enable various other use cases, including bullet trains, sports broadcast. FIFA is coming to KSA, so 6G will be very important to do this live broadcast. So in our hub, we are working on technologies which can enable 6G. So 6G will not be out until 2032, 2033, but we need to develop the technology. No, use case is set up, KPIs are set up, so work is being done on development. So we work on developing antennas. No wireless is possible without antennas. So antennas are ears and eyes of any wireless communication system. We work on intelligent reflective surfaces, we work on quantum communication, but focus of this talk will be on this. So the prospective band to be used for 6G will be terahertz, because it can provide us the features like peak data rate up to 1 terabits per second and latency less than 0.1 millisecond. But it comes with challenges. So terahertz has challenges around atmospheric absorption, that it is very sensitive to moisture contents. Second is skin depth. So as you move higher in frequencies, yeah, it is. As you move higher in frequencies, what happens is that skin depth decreases. So it means we cannot use conventional materials for 6G. So we need to have some new 2D materials which can enable 6G. So in our hub, we are trying to look at some novel new 2D materials, which includes graphene, carbon nanotube. Just listen to me, it's okay,
Right,
don't
right,
worry
right.
about that.
Yes, yes.
So it includes graphene. No, I'll keep you entertaining, you don't need slides. So
One sense then.
yeah.
You need two senses at least.
So, but I can make it happen in one sense as well. So 2D materials like graphene, carbon nanotube, we are using those materials to make antennas. And they have a special phenomena called surface plasmon phenomena. Focus here, forget about projector. So they have surface plasmon phenomena which can help to overcome the challenges posed by terahertz. So in our lab, we have developed various kind of terahertz antennas. Sure. We have developed various terahertz antennas which can help us to achieve the vision for 6G. And these are world first antennas we have made, which were of sub nanometer scale, for example, equals to this nail size. And okay, it's here. Okay. So we have made these antennas. As you can see, these are world first antennas which were being simulated, fabricated and mired as well. And we were able to do these because we have world class facilities where we have a clean room 1400 meters square, and also we have characterization facilities going from 10 megahertz up to 1.1 terahertz. So UK government recently funded a 6G cluster where we can generate 6G signal and test it as well. So let's come to the main thing, which is these reconfigurable intelligent surfaces. So let me explain you first what this is. So this is Hunterian Museum in the University of Glasgow. Imagine we have one mobile user who is using the phone, right? So whatever signal is coming to this user, there is no direct path. So we have reflection, scattering and diffraction. So ultimately the quality of service reduces. But imagine if I put something on a wall which focus all those signals to the user, so ultimately what will happen? The signal quality will increase. So the concept is similar to mirrors. So if you have a sunlight, you can use mirrors to control light. So similarly, these surfaces are mirrors for electromagnetic waves. So you can use these surfaces to control electromagnetic waves. And they have applications in all domain of life, starting from healthcare to airports to train stations. So I will give you an example of sensing for health later on. And we have developed world-class, world-first reconfigurable intelligent surfaces covering all the spectrum going from 5G, which is 3.75 gigahertz, to X-band, which is used by defense, to terahertz, which will be used in 6G. So I'll talk about these designs briefly in next few slides. But the point is that we cover all the spectrum. So this is our first test bed. Basically, this is a 1-bit intelligent reflective surface. When I say 1 bit, it means that it can change the phase of incoming wave by 180 degree. So how we made it? We made a meta cell which is on the right top, and once it's being designed, then you replicate it to make a tile. And the reason to make tile is that you have flexibility, that you put tiles in a way you like you put tiles on the floor. So we have made this structure so that you can make any shape, cascaded, parallel, hybrid, small, big, whatever you want. And this is basically what this surface is doing. It is switching, as I told you, changing the phase of the incoming signal. So how it achieved this? By using some switching element. So we had pin diode in this case. So this is our first test bed, which has 4096 elements. It is one of the largest test bed available globally, and it can provide us a gain, a very high gain. I'll talk about that. But one thing, students, you need to remember is the power consumption for this whole test bed was 15 watts, and I'll ask you later on. So the second test bed we made was a 3-bit metasurface or RIS design. By 3-bit I means 2 raised to the power 3 states, in total 8 states. So you can change the phase of incoming signal by 45-degree steps, 45, minus 45, 90, minus 90, and so on. So again, process was similar. We made a single meta cell, and then we made a tile, and you can see in this figure we had 6 tiles. One second, what is this? There was something coming. So we had 6 tiles. I think it should be fine. And we were controlling this architecture by using FPGA, because FPGA is the brain which gives these configurations to turn on or turn off certain element. So this is the actual hardware which we have developed. Now we have designed the hardware, right? We want to test whether it serves the purpose or not, because one of the main benefit of these surfaces is to provide gain, reduce losses. So we took this to anechoic chamber. Anechoic chamber is a shielded environment where there are no external reflections. So we tested our 3-bit RIS, and you can see the bottom figure. We have a close agreement between simulation and measurement, where we were able to achieve 8 different states.
8 different states?
Yes, 2 raised to the power 3, different angles, 45 degree, minus 45. So this is, and now we want to test that really this technology works or not, right? It was working in a special environment, which was a chamber. So now we want to see if it works in a real indoor environment. So we designed an experiment for various indoor environments, including lobby, multi-floor, corridor junction, where transmitter was placed at one location and receiver was placed at 4 different locations, 1, 2, 3, 4, where they cannot see each other. And then we placed this RIS in the middle. So if there was no RIS, there will be no signal coming. So we placed it for various scenarios, and results were very encouraging. It was showing a gain of 20 dB on average.
Improvement in power.
Yes, improvement in received signal by 20 dB, which is very high. And we were working with British Telecom, which is one of the largest telecom operator, and we got super excited. We went to them, oh, we did a breakthrough, look, it's working. And they asked us a question, what is the total power consumption? Can somebody tell me what was the total power consumption?
15 watts. 15 watts.
Yes. So they said this is very, very high, because imagine if you want to make a big system, 15 watt power is very high, and if you want to replicate it, it costs them millions. So they even do not want to invest a single dollar. To switching the element. Heat is another thing, but power consumption is another thing. So they said to us,
Cold weather, you can use it for
heating homes, yeah, but you have to provide the energy. So then as a researcher, we got demotivated. What should we do? Because our years of service got wasted. But then as a researcher, you shouldn't get disappointed. So we started thinking again, and we came to know that the main power consumption was coming from those pin diodes, switching elements. So I'm sure we all have studied varactor diodes. So the beauty of varactor diodes is that they work in reverse bias, means they do not consume any power or current. So we made a new design where we use varactor diodes for switching instead of pin diodes. So ultimately power consumption reduced from watts up to few milliwatts. So this was one thing we got by using varactor diodes, and second thing was we were able to steer the beam, because in varactor diodes what you do, you change the voltage, you can change the capacitance. So if you change that, you can switch the beams. So we showed that in addition to sending beams at fixed angle, you can do beam sweeping or beam forming as well. So we were able to do from 0 to 180 degree, but this was in simulation. So we went to University of Southern California to use their channel sounder to do actual measurements, and you can see there is a close agreement between simulation and measurement. Then we work a lot with our other defense department as well. So where the idea was to make these reconfigurable surfaces at 5.8 gigahertz for outdoor environment, where we try to make it flexible. And this was a new design which was being developed at 5.8 gigahertz. I cannot tell more because it's related to defense. And then if you remember, I told you a very unique feature of 6G, which is joint sensing and communication, doing both sensing and communication. So what we did, that we designed these RIS surfaces at X band. X band is basically 8 to 12 gigahertz, which is being used by radar, some of the radars. So we were using those radars for sensing and for communication as well. But as I told you that if there is non-line of sight scenario, you cannot do communication. So we need to make these X band RIS, where process was similar. We made a unit cell, and then we designed a tile, and also you can see that in 3D model the circuitry is brought to the bottom. And the advantage of this was that our previous designs were consuming around 20 millisecond switching speed. They had a switching speed of 20 millisecond, but here we reduced switching speed to 0.5 microsecond because of efficient circuitry.
So you sweep the phase shifts, and do you get feedback from the receiver that this is the best phase shift?
So what we do is basically we have a PSO algorithm running which scans the beam continuously and look at the maximum SNR. So wherever we are getting maximum SNR for receiver, we transmit the signal in that direction. No, there is no backup from receiver, no. So it is scanning by finding a location where we have maximum SNR going out. So we are not getting that. So then,
but then how do you decide where to focus the beam?
Yeah, this is basically PSO algorithm which is continuously scanning that where we have less noise, more signal to noise ratio. So in that case, we conclude that this direction we can get a maximum SNR, it means receive power will be the maximum. So we focus on that direction.
But shouldn't you do it the other way around? Where is the weak spot? I should focus my beam there.
Towards the receiver side, right?
Yes.
Yeah. So no, this is basically the scanning where we have a less noise. It means, of course, we're going to send to the receiver where it is being required. For example, you three are receivers, right? And one of you needs a signal, others does not need it, right? So based on that, we have a closed loop going on where we focus the beam towards that demanding user. And I got your point towards the weak as well. It's not compulsory that it needs to be a weak signal location where you send the signal. But that is a good option.
It means that you have the feedback from the users to tell which user needs
This is a big term goal. This is the big term. But currently we have a fixed spots where we are doing, because we are making an AI algorithm to do it. But the answer is currently we don't have. But this is the ultimate goal. Then
you can adapt the power to serve all users.
Sorry?
You can adapt the power.
Yes.
Different pins to serve multiple users.
Yes, we can do that.
Same level.
Yes, we can do. Yeah.
Do you create multiple beams here?
Yes, we had. No, it was a beam forming. So at one time we are doing beam scanning actually.
Yes.
Yeah.
But at once, you will focus on one beam on one, no multiple beams here.
No. So currently the goal is one user will get the maximum signal the main beam width, but others have some beams as well, but that is low power. Yeah.
Why not create different beams to serve number of users?
Yes,
Have the power.
absolutely. That is the ultimate goal, but it's work in progress. So the ultimate goal for RIS is that I place it on a wall, okay? It uses its own brain by looking at the environment, getting feedback from both transmitter receiver to make multiple beams, giving signal to whoever wants it at whatever power level they want. But this is a big goal, which is still not done.
Can be adapted accordingly.
Yes, yeah, this is the big goal.
But your current limitation is from the number of bits of switching.
Yes.
You want to increase that, then you can have
Absolutely, absolutely. Yeah, because it's a trade-off. You know, when you have more basically bit or quantization, you need more pin diodes, you need more switching elements, more complexity. So it's a trade-off. Sorry, you was asking something.
Let's
Finish. Okay. Okay. So then the last one other RIS we made was static transparent RIS. So the idea is that you can place a sticker on a window, and window remains transparent, and then you can get all the signals coming to inside the environment, whatever you want. So we were using silver nanowires, and we can get a beam switching from 10 to 40 degree. And this is my latest project, which just started, which is basically we were talking about RTDs. So the idea is that how we can get, because when you go higher frequencies, losses are higher. So we switch to active RIS, where we are working with colleagues who are working on RTD and TMO material. So the idea is that we put these amplifiers on unit cells so that we can amplify the signal as well. And this is just funded 2 months ago, but we are working at 100 gigahertz to make these RTD and TMO enabled RIS. I'll skip this optical RIS. But we also look at, I know there are some signal processing guys as well. So we are not only working on developing these surfaces, but we are trying to look at fundamental issues as well. So one of the challenge is mutual coupling between those elements and EMI. So the issue is that if you look at the top figure, the dark lines are basically when we are considering our switches without any mutual coupling. But when we consider mutual coupling, what happens is that capacitance changes. And you can see that peak data rate drops significantly. So the people who are out working on this, they are ignoring these fundamental challenges, which is mutual coupling and electromagnetic interference. So we are basically working on this where we have developed an iterative algorithm where you can, this is what Professor you was saying, we distribute the power as per the user requirement so that we can reduce EMI and mutual coupling issues. And you can see in the slide that we are very close, our iterative algorithm is very close to considering it with EMI. So this demo will show you what actually our RIS is doing. This is a bit old video. Oh, there is no volume, but I can explain.
Is that your twin brother?
It was me during pandemic. So what we are trying to do here is doing a video demonstration over the RIS. So this is, I'm just explaining the RIS we developed. I already explained it. So what we are doing here is that you see transmitter is in one room, receiver in another room. They cannot see each other. We want to transmit the video by using this RIS. So you will see that when RIS is off, we didn't configure it, the power levels are so low. So we cannot receive the video because there was no direct line of sight between transmitter and receiver. You see power levels are so low. So as soon as we will configure our RIS, you can see that power levels are going up. and ultimately video will start streaming. See, video started streaming. So we were getting an average power increase of 20 dB. And this is the RIS phase distribution demo. This is basically representing that how a wave is moving from 0 degree, you can see 90, 180, 270 and so on.
This is how many bits?
This is 1 bit. And then I was delivering talk in one of the conferences and somebody said to me, oh, your RIS gain you showed, it is by using horn antennas, directional antennas, and it was a very controlled experiment. So it was very obvious that you will get gain. So as a researcher again we got demotivated, but we didn't give up. So we went back and we did world first outdoor trials with a commercial network by using this RIS technology. So this is the mast of British Telecom, where we were basically, this is the mast which you all have seen, and these were the antennas they use at receiver side. So what we did that we designed an experiment. This green circle is a transmitter, which is this, and then we defined two zones, A and B, and we placed our RIS over there with receivers at different locations to see if this will work in a commercial network or not. So it's needless to say it took us months to plan these experiments and so on. But what is important are results. So this is zone A, where left hand side is when there was no RIS, the power levels were low, but the right one is optimized, it means we have got a gain. So for 3 different locations, 1, 2 and 3, we were getting an average gain from 5 to 15 dB, and at 33.6 dBm there was 50% capacity increase, which proved our point that these RIS surfaces works very well in an outdoor commercial network as well, with a gain of around 10 to 15 dB. So this was all about RIS in communication, that how we were using it in communication. But the second application we work on is sensing. So the future is that currently what is happening, we go to doctor, they ask us about our health parameters and then they prescribe something. So this is called doctor based healthcare. But no, we have mobile phones, we have smart watches. So we want to control our health ourselves. So this is called patient centric healthcare. The idea is that we move from doctor centric healthcare to patient centric healthcare by having smart homes. So in future I'm going to have home which has various kind of sensors in it, which has wearable sensors, environmental sensors, nanoscale sensors. These all sensors will collect information together, send it to cloud, where we will apply machine learning and deep learning to the data, and then we can take proactive decision. Proactive means we can take decision before something happens. So this is the vision for future healthcare. So I myself work on wearable sensors, RFID technology as well, but I'll not focusing on that. I will focus on a special kind of sensing which is called contactless sensing. The idea is that we have radio frequency signals around us, right? We have Wi-Fi mobile signals. So can we use those signals to monitor people? Yes. So we were using those signals from last 10 years to monitor people, but one of the challenge with that contactless sensing is that the user needs to be in between transmitter and receiver, number one. The second challenge was resolution, because RF waves are ambient. Third problem was if someone stood up and go out, you cannot track the target. So there were certain limitations with current contactless sensing. So what we did was that we used these reconfigurable intelligent surfaces and published in Nature basically, where the idea was that we can control electromagnetic waves to focus on the user. So ultimately we can increase resolution, we can localize the target, and we can have this sensing in non-line of sight scenario as well. So details are in the paper. So we did these world first experiments to prove that this works by designing an experiment where transmitter and receiver were unable to see each other, user was performing some activities near the transmitter, various scenarios, but the results were interesting. So when this surface was off, we cannot see any activity. But when we turned on our surfaces, we were able to detect these activities with 100% accuracy. So this was 3 years old, but we have progressed a lot. Then the second thing, again, we published this work in Nature. This is very interesting. So we humans, you have seen around your families or somewhere where people have hearing issues. So they wear hearing aid devices, but those devices have a phenomena called cocktail effect. Cocktail effect is that those hearing device noise level are trained for certain environment. See, this is very calm environment, that will work, but if you go outside, it might not work when it's noisy because those noise level are not adjusted accordingly. And they hate to wear these devices because if you ask them, it's a very painful noise, which is called cocktail effect. So what we thought, let's make an intelligent hearing aid device. So we humans have brains, right? Your brain is interpreting information, what I'm saying, not only based on my audio. It's listening to my audio, looking at my body language, looking at slides, combining all that information and converting it to useful information. So we thought the same concept, that can we make hearing aid devices intelligent, where we take multimodal information, audio, lip movement, facial expressions, combine all those so that device can adjust the noise threshold level. Ultimately, cocktail effect will be reduced. But so what we did, we basically, during the pandemic, a challenge came that everyone was wearing a mask. So there was a Google technology which was reading the lip movement through camera, but if someone is wearing mask, you cannot read the lip movement. But RF waves can penetrate, so we use this to read the lip movement for the first time. Ultimately, we prove that we can read somebody's sentences, what they are saying, by using these radio waves with an accuracy of more than 80%. And then we have so much progressed in it where we are using some kind of RIS surfaces in a mask to focus the beam. And then these RIS surfaces were being used to monitor people heart rate and breathing rate as well for non-line of sight scenario, where we compared our work with off-the-shelf breathing and heart rate sensors, where the error was only 1%. And then this is brain-computer communication. So what we did, that again we published all this work in Nature. If you are interested, you can go there. So we were using these surfaces to do brain-computer communication, where we were taking one user information through BCI, transmitting it over RIS, and receiving it on the other side. The last bit for my presentation is about localization. So we talked about RIS for communication, RIS for sensing, and the next thing is localization. We all know that localization has so many benefits, including navigation and wayfinding, asset tracking. So what we did was that we proved that, you all know that GPS does not work inside, right? So we showed that if we put these surfaces on a window glass or somewhere, basically we can do indoor localization with very high accuracy. So we published this again in Nature. So what we did, we developed a controlled experiment for where users were placed at 9 different locations with a spacing of 0.5 meter. And I'll skip the details of the experiment, but the key was that we were able to detect the location with an accuracy of more than 84%, which is again work in progress. And then we were using this RIS for V2X security and so on. But I'll close my talk with this demo, which is the key feature for 6G, which is joint sensing and communication, that how you can do both sensing and communication by using same frequency, same system. And the benefits are so many because it will provide spectrum efficiency, cost saving, security and privacy. So how we demonstrated it, that we had 2 users, we measured their vitals, and also this is basically sensing, and we also use same frequency to transmit that data as well, which was communication. And this was world first demonstration to prove that we can do joint sensing and communication. So this is the demo. So you can see that on the upper figure we have spectrograms. So 2 users are static. So the spectrogram is basically embedded heart rate and breathing rate for the users, and we have a read range curve at the bottom in figure 4. You will see when users are moving, that spectrum is shifting. So this is basically communication, and the upper one is sensing their vital parameters. And this video will show you another joint sensing and communication feature, where you can see that in the video, this is communication. We are communicating the video in real time, and then left side is activity, where there is no activity. Why it's not working? Yeah, it's working. So you will see that when user is sitting, there is no activity being detected. As soon as user will stand up, you will see that activity has changed to standing. So we are doing sensing, which is activity, and we are transmitting video, which is communication. So this is, we are using same channel for sensing and communication. So I think I was thinking what to put in summary, but the conclusion is the future is here, and we all need to work together to make this future happen. We have so much outside which you can see to read, and I would like to thank all my collaborators, especially students and external funders who helped me to do all the work I showed, and thank you for listening.
Thank you, Professor. Thank you very much for this very interesting talk. I think even time-wise, I don't want to take too long of everybody's time, but we'll take a couple of questions if you would like to ask any questions. Yeah, we'll take a couple of questions, and please allow me to interrupt whenever it's time. So let's begin with Dr. Hatem. Sorry, Dr. Rabah.
First, thank you so much for the very informative lecture about the smart surface that you use. How big is that one? How many cells inside? What is the speed of the pin diodes or the Baractor diodes? Can you replace these diodes with MIMS, for example, instead of the other things? Whether the transmitter, is it just one transmitter and many receivers, or there are multiple input,
MIMO.
okay? This is the question that.
So
Yes.
very good question. So the main cost and hurdle for this technology to come to market is these switching elements. So people have used PIN diode, people have used varactor diodes, people have used MEMS. But what we are now doing is we are using ink, because these switches cost. One MEMS switch will cost around $10. You go higher in frequency, it gets expensive and expensive. So what we are doing now is you make these surfaces for switching, you put an ink. Basically we are working with some material collaborators. I don't do this work. So that will work as a switching element, that you change the voltage or temperature to turn on or turn off those switches. But the challenge there is that when you are using ink, the efficiency reduces. But there is a trade-off.
Okay.
So the operators and vendors with whom we are working, they say that if you can reduce cost significantly, we can compromise on the performance. Yeah.
Perfect. Another question. Does anyone have any questions? Yeah, please go ahead.
Yeah.
So as I saw in the slide, there was a reference about mining or receiving data underground. Is it actually capable, or this panel is actually capable of transmitting data underground? Or?
Under the ground.
Yeah. There was a reference about the miner that receiving data on the last
Yeah, so the point is that, it is directly related to frequency. Lower is the frequency, higher is the wavelength. So penetration is linked to that. So we can go up to certain thickness based on the frequency we are using. For example, for terahertz, because I work a lot on healthcare, so we use it for skin, you can go only up to 3 millimeter inside the skin. So it's a trade-off again.
Right, right. Time. Another question, Dr. Joe? Yes.
First of all, I would like to thank you very much. And you're absolutely most welcome at our beloved department and beloved university. And we hope to host you again also, and we hope that you can join our department as a faculty member.
Thank you.
Like
Thank you.
Dr. Sami said earlier. I have 2 points actually. One of them is this surface, when we put it somewhere, would it stop the passing of a signal from the other side? Because would it allow the signal to go through, or penetrate or not? Okay. And on what basis you choose where to place it?
Very good question. Very good and very difficult question. First question was easy. So there are 3 kind of RIS. One is called reflective RIS, which I presented. Second is called star RIS, which is simultaneous transmission and reflection. And third is transmission, the one I was showing you for the transparent one. So this one was reflective, so it will not let pass. But if we use transmissive or star, we can let it pass. This was first question. The second one was related to, sorry, where to position it. Yes. This is very critical thing, yeah. So, you know, these surfaces are helpful only if you have, there is no direct path between transmitter and receiver. For example, I can talk to you directly and I put RIS here, there is no benefit, right? So, it needs a survey to see where we have not spots, means where there is no coverage. So they are usually placed there. This is the goal. So in basically British Telecom outdoor survey, we have to do this to find areas where there are not spots, so we place them there. So location is very important.
So you probably need like a huge data to analyze, and a huge surveying, and some data that you need to collect.
Absolutely. So it's very similar. Yeah, it's very similar to these mobile operator put basically repeaters.
Right.
And before that, they do site surveys.
Okay.
So you do that and you collect the data.
Perfect. We'll have a couple of questions as well. Dr. Ghafar, please.
Thank you very much for a wonderful presentation. I have 2 small questions. One is that without reconfiguration, can we just put a passive FSS or passive reflector to do the same job, to reduce the power? And the second thing is for lower frequencies, if the unit cell become very big, that means that the number of diodes will go down. So is it possible for this sort of screens that maybe for lower frequency the power used is less, but when we go to the higher frequency, the number of the unit cell will become increased, and then the diode and eventually the pin diodes and vectors.
Very good question. So I can answer to the second question about low frequency. Basically, these surfaces are the gain works if receiver is in far field. If it's not in far field, which is 2d square by lambda, which is basically directly proportional to the distance and the wavelength. So if it's not in far field, then there will be no benefit. So if you are in lower frequencies, the size will be so big and far field will increase as well. So you cannot use that for the applications for indoor, for example, if we are at very low frequency. That's why we are moving to very high frequencies. So that is a big challenge, basically, that can we make them smaller, electrically and physically smaller at lower frequency. This is an open area, because these RIS surfaces area started back 5 years ago. So there is so many research going on.
But again, I think it is related to the scope of the 6G that you are doing,
yes,
right? So that's what you are interested in, more or less. Dr. Lutfi will have a question.
Oh yeah.
Okay.
I was going to say, yeah.
Please.
Dr. Abbasi is also chair of young
Professional, yeah.
for Antenna and Propagation Society.
Salam.
Yeah. So we are willing to have our chapter here at Tigabla University in our college for the students. The registration of this event is $1 because the chapter has 75 years
Anniversary, yeah.
Exactly, yes.
Yeah.
Can you talk,
Yeah, I'll explain.
Yes.
Yes, I'll explain that. So, thank you for reminding.
Great man.
Yeah. So I am basically IEEE Antenna and Propagation Society and IEEE Microwave Theory and Techniques Society Chair for Young Professional. So we have around 400,000 IEEE members around the world, and the benefit of joining IEEE Society is to have access to knowledge, access to networking, access to scholarships. So they fund you to do any kind of projects, any kind of activities. For example, if you have a chapter, you can invite speakers like me from around the world. They pay, they come and they deliver you lecture. They can do workshops for you. And then, as I said, most important thing is networking. You will be able to connect to students and researchers from around the world, and you will get a knowledge. Yes. And because APS Society became 75-year-old last year, so they have reduced the registration only for students, not for faculty,
Yes, okay.
to $1. You pay $1. You are a senior student, only for young students.
Right.
So you pay $1 and you get the membership. And trust me, when I was student, I thought it's a waste of money, but that's very important.
Yes.
The key to success in this world is networking.
Right.
So that IEEE Society will provide you access. So please do it. Next year, there will be a very big IEEE conferences coming to Jeddah, where your department will be involved as well, and it will give you more access to knowledge.
This is actually a perfect timing.
They need to be IEEE members first.
Yes.
Before
Yes.
joining the society.
Yeah, they can just be an IEEE members, and then they can just join the society.
$1
For the society. Yeah.
And it's $15 for student.
Yeah, it's
for,
not that.
For young students, only $15.
Yeah. Actually, this is the perfect timing because we are about to reactivate the student, the IEEE student.
The usual fee is how many limit? Is there any time limit?
For this one? Yeah.
No, anytime.
This year.
Yes.
Anytime you can. Yes.
Right. Yes, we'll come to your question.
Yeah, you can talk to Professor anytime if you
I
have any
think
question.
for students, if you have seen some of the ads that was circulated about the IEEE branch, student branch is being created. So if you have any questions, please reach to them. And you can even ask them if you want to start or begin this chapter or this society here in the university, you can easily do that. Just as the guys who are taking the responsibility for the student branch, how do they do it? How did they activate the student branch? You can activate and start your own society or a branch of that society inside King Abdulaziz University. So please feel free to do that. We'll take a last question from Dr. Ahmed Ben Amish. And I'm sorry, I skipped the first time and I'm again. Sorry, we'll take another question also from Dr. Khalid, inshallah. Prof. Khalid. Prof. Ahmed?
In the sensing experiments, were you doing active radar sensing or passive or both?
Passive. It was passive, yeah.
But the resolution seems to be impressive. With a passive radar is uncontrolled, the signal is not controllable. So are you really having a good signal?
No. So a very good question. So what we were doing was initially no RIS. Okay. So the problem is when it's non-line of sight between transmitter and receiver. Okay. So we placed a RIS. It focused the beam ultimately on the receiver. So goes to RIS, goes to receiver. So it's like a line of sight. Ultimately, performance improved.
But
yes.
It's in the passive radar scenario, even the best performance is not that good. So what happens here?
No, because it was non-line of sight for passive radar.
So are you benefiting from that? Now you know the direction of the
yes.
of the
angle. Yes. We were basically focusing the beam in such an angle that it looks like a line of sight to transmitter and receiver. Previously, it was only reflections going to receiver, so it was not working.
Yes. طيب, Dr. Khalid?
Thank you very much. Very interesting. Actually, I have several questions, but I will.
We can
Yeah,
chat.
go ahead. Go
Yeah.
ahead.
I think he's from Glasgow.
Are you from Glasgow? No.
Dr. Khalid Munawar? No, I didn't think so.
No, I thought Khalid Harbi.
No, Khalid Munawar. Khalid.
Okay, about these surfaces, how do you decide the number of elements? This is one question, and what I feel is that if really you are going to establish a communication link, then definitely you need a bigger array. But the application that you talked about, the telecommunication, means you have what you can say an uncovered area where you really want to direct your communication, means it is like a broadcast sort of thing. So in that case, isn't it good that you should really have very few number of elements that would make the antenna of the surface important?
Very good question. So this I know communication theory people, what they do, they just put 4, 6, 7, 8 element assumption and do simulations. But in reality, if you want to get a gain, you need to have more elements. Because we had a tile based approach. So with one tile we were getting only 3 to 4 dB gain.
But isn't it going to means increase the directivity also?
Yes, it increases.
How then you are going to cover the area?
So this is basically the big picture is that different tiles will be focusing beam in different directions. So the purpose is to serve multi-user scenario, right? So if we do not have various elements, large number of elements, you cannot have multi-user scenario, you cannot provide maximum gain because all these signals add up to provide the gain. So it is a trade-off. So there is not an exact number that how many you need, it depends on how many users are in that area and how much gain you need.
Could not it be a hybrid approach, means for example means you have a crude array that really focuses a very weak signal to a hidden area,
Yeah,
and then you have the better arrays that really give you the gain.
I think that's a very good option, but we are looking at these things slowly. As I mentioned that there are so many open questions.
Right.
We cannot claim we have done everything.
And that's what research is all
Yes.
about. If you are doing research, you will have a huge number of issues that you need to tackle, but you cannot tackle all of them at once.
Absolutely.
You tackle them one by one until
Yeah.
you reach to
Yeah.
a mature results. So thank you again
Thank
very
you.
much, Professor
Thank you
Qamar,
everyone
for
for
your
listening.
talk and for coming and for visiting us. Thank you to all for your attendance and for your valuable and important questions. And
You can email me if you have any
yes,
question. I always
Dr.
reply.
Qamar's contact will be shared with everybody if you have any questions. So again, thank you again to Dr. Qamar for this talk, and we'll see you inshallah.
Group picture.